intercept and coefficient estimates. So the coefficient estimate, the alpha and the beta, is often called the point estimate. It's the value that we estimate from the model. And these are the alpha and betas that are produced by this OLS, ordinary least squares regression. The question is, does this factor that we've chosen actually describe returns? Is there a statistically significant relationship between the factor and the asset and the portfolio? Is there a statistically significant relationship between the factor and the asset, or the factor or the portfolio, depending on what we're regressing? In other words, given the estimated alpha and beta, how likely is it that the true relationship between alpha and beta is 0? Because we've just sampled some data and we're trying to estimate the true relationship. So here's how it works. We have to overcome this null hypothesis. The null hypothesis is that there is no relationship between the factor and the asset. The market does not describe the returns of the asset, the returns of the market. Later, we'll have things that might be more in question, like, is it the case that this particular stock's return is described by energy prices, or is described by exchange rates or interest rates or some other factor? So what we're doing is we're looking for evidence that allows us to reject the null hypothesis of no relationship and therefore accept the alternative hypothesis that there is a relationship. And to do this, we're going to look at the t-statistic and the p-value. So the Excel regression function produces two important values. It produces the coefficient estimate and it produces the standard error of the coefficient. And it also calculates the t-statistic. The t-statistic is the ratio of these things, the coefficient divided by the standard error. And so we can think about a t-statistic as kind of like a z-score. So if you recall the z-score when we were looking at confidence intervals, we looked at z as some arbitrary x minus the mean divided by the standard deviation. And if x was equal to 0, then z is equal to minus mu divided by sigma. And what this is essentially telling us is the number of standard deviations between this estimated mu and 0, because we've essentially plugged in 0 for x. And so you can recall this example from chapter 5 where we had mu equal to 10% and the standard deviation equal to 20%. And so for x equal to 0, the z-score is equal to minus mu divided by the standard deviation is minus 10 divided by 20, and we get half for our z-score. And the way to interpret this is that the mean, 10%, is half of a standard deviation, which is 20% away from 0. And the question is, we expect a return of 10%, but how likely are we to actually have a return of 0? Well, let's take a look. We use the cumulative normal distribution function, the norm sdist function in Excel, and we get 0.3085. And this is also this integration. I can plug it into this goofy function and integrate, and I'm going to get 0.0385. Of course, it's in Excel, so we don't bother. But what this means is that 30.85% of this curve, remember the value under this curve is 1, 30% of it is shaded. So even though I expect a 10% return, there's a 30.85% chance that the actual value will be less than 0. And there's a 69.15% chance that the expected value will be greater than 0. So now I'm doing something different with the same statistical tools. Now I'm going to have an estimate of my beta at 0.1, and I'm going to have a standard error of my beta at 0.2, and the question is, how likely is it that the 0.1 that I just came up with as an estimate, how likely is that that's really 0, that there actually is no relationship? And so in this particular case, if that were my beta and it were my standard error, then there'd be a 30% chance that this number that I calculated is actually 0 or less than 0. That's not a very strong level of statistical significance. So what we want to do is compare the z-score to the t-statistic and the p-value to the norm sdist value. So here's the idea. Similar to the z-score for x equal to 0, the t-stat is the number of standard errors between the coefficient that we estimated, either alpha or beta, and 0. And similar to the norm S-dist value, the p-value is the area of the curve past zero. How much of the curve is past zero, and how likely is it that this number that I estimated is really zero? Now, another small difference between what we did earlier and what we're going to do now is that the coefficient estimates are sampled from a distribution of coefficient estimates with an unknown standard deviation. And so therefore we're going to use a t-distribution, not a normal distribution, and Excel will do that for us. So essentially the p-value that we calculate is effectively the tail area in the t-distribution for this t-stat. Very similar to the same way that the norm.s.dist value was the tail area for the normal distribution. So we'll use the t-distribution, not normal, but the interpretation is the same. And so the idea is the probability of observing the estimated value that we get. If it's really zero, that's how we interpret this p-value. So if I get a p-value of 0.05, then there is a 5% chance of observing the value that I estimated. If it really is zero, I can be 95% confident that this thing isn't zero. But if I get a p-value of 0.3 or 30%, then there's a 30% probability that the estimated value is really zero. I'm only 70% confident, and that's not going to be enough. For the purposes of this class, we will arbitrarily and consistently look for 95% confidence when we look at these things. That's just going to be an arbitrary but consistent number. We'll always have that be a cutoff. And so the idea is that we will reject the null, that alpha and beta are equal to zero with 98% confidence if the p-value is less than, is 0.05 or less. And remember, the idea is that we're looking for evidence to reject the null, which is there is no relationship, and conclude that there is a relationship. And so we're going to go back to our McDonald's regression. We're going to look at the R squared and the adjusted R squared. We're going to look at how much of the variation of returns are explained by the factor or factors. We're going to look at beta and its p-value to determine if this factor, which in this case is the market, is a priced factor. And we're going to look at alpha and its p-value to see if there really was risk-adjusted excess returns. And so let's go to the spreadsheet.